So we have V is a vector space with a inner product defined. Now, as you can tell from the examples on 5.4, the inner product tweaks, right? Every different vector space picks a different inner product. Sometimes they pick a weighted inner product. Sometimes they pick a non-weighted inner product. They kind of just go through it. When we actually see all of this, we normally just simply say V is an inner product space. The problem with just simply saying V is an inner product space is sometimes it leaves it open-ended to when you have a particular example, it's, well, what inner product are you talking about? It's like, I know you're talking about Rn, but what inner product are you using for this particular Rn? Because you have to have that come along. And sometimes it's like, well, we pick the natural one, or they don't tell you, and you just have to kind of figure it out. When you're going through this, we'll just say inner product space. But when I say inner product space, in the back of your mind, you have to think, I wonder what inner product he's using. Is he using a weighted one? Is he using a not? I mean, what is actually he using? And it doesn't really matter if I don't do a specific example, but when I do an example, it'll become important. It's like, which one are you actually talking about? But if we have an inner product space, we have an inner product. That means that we can look at a set. Let's say I have a set V1, V2, up to Vk. So I have k vectors within this inner product space. And then I go through it and I check that when I do any two of these such that they're different from each other, right? Just like you did with the sine and the cosine example that was asked, right? If I pick they're different. So if I pick sine 2x, I mean sine 3x. If I mean cosine mx, I mean sine mx. The different ones, if all these are true, it's 0. Now, if an inner product is 0, that really means what? I could have, instead of writing it this way, what could I have actually written? That Vi is orthogonal to Vj when I is not j. So just saying that their inner product is 0 is just simply saying the word orthogonal. If this is true, we'll simply call V1, V2, up to Vk an orthogonal set. So when I say the word orthogonal all by itself, it normally says that this vector and this vector inner product is 0. If I say orthogonal set, I really mean that, when I check the orthogonality from every vector to every other vector, I always get an inner product of 0. And then I'll just simply say the entire set is orthogonal. An example of that would be, let's say I'm doing continuous functional space from -1 to 1 with my inner product defined as to be a non-weighted integral from 1 to 1 of f g dx. Consider, say, polynomial 1, function of x is 1. Polynomial 2 is a function of x is x. Polynomial 3 is a function of x is 3x squared minus 1. So I have these three polynomials. And I could check it and say, hey, what's the inner product from P1 to P2? Well, that's just the integral from -1 to 1 of 1 times x of x dx. X is a what function? Even or odd? It's odd because its power is odd. So the integral of an odd function from -1 to 1 is simply going to be what? 0. And you could check it, right? 1/2 x squared from -1 to 1 is going to be 1/2 minus 1/2 and get 0 out of it. And then P1 to P2. Well, that's just 1 times that. So it's the integral from -1 to 1 of 3x squared minus 1 dx. That I'm going to have to integrate. What's the integral of 3x squared? Integral of 1? Plug a 1 in on this first part, what do I get? 0. Minus, plug a negative 1 in, what do I get? 0. And so it's 0 minus 0, which is 0. So P1 and P3 are orthogonal. And then I just have to check what? P2 and P3, which is going to be the integral from negative 1 to 1 of x times that is 3x cubed minus x dx. What's all powers? Odd. 0. You can integrate it, but it's all odd, 0. We're good. Is everybody okay with that?
It looks like on the second one you have P1 and P2.
3. And that doesn't look like a 3 either. 3. So this set of polynomials are what? They're orthogonal. And so 1x and 3x squared minus 1 are an orthogonal set. You just check. You just check the inner product on every combination that you could do. If they're all 0, they're orthogonal. Yep.
Would those then be a basis? If it's
if I would take the span of these polynomials, and the span of these polynomials, right, it would be a basis for the span. Right? And that's actually why are we interested in orthogonal sets? We're interested in orthogonal sets if the V1, V2 up to Vk are an orthogonal set that actually says that they are, the VI are, not only are they orthogonal to one another, they're linearly independent. But if they're linearly independent, they start to form a basis for their span. Why would they be linearly independent? Well, what would be the idea behind that proof? How do you show linear independence?
Then no part of, or no combination of the vectors.
So what we check for what? We take C1, V1 plus C2, V2 plus everything up to CK, VK equals 0. What do? We look at the homogeneous system and check if they're independent when what? It has only the trivial solution, right? So if this only has the trivial solution, then it would be independent. Well, if this is true, right, which is what we have, right, we're saying solve the homogeneous system. If the left is equal to the right, that would actually say that if I would take any one of the vectors, say vi, and say, hey, what would be vi compared to the left side? C1, V1 plus C2, V2 plus everything up to CK, VK. Okay, the linear combination has to be the inner product of vi and 0. If they're equal, their inner products have to be equal. Well, that's pretty easy. What's all vectors inner product with a 0 vector? 0. Now, what's the nice thing about inner products? They have linear combinations, so that would mean that this is actually C1. What's the inner product between VI and V1? Plus C2. What's the inner product from VI and V2? Plus CK. What's the inner product from VI to VK? What do I know about all these vectors? They're orthogonal. So what's their inner products? 0, except for when it is what? Literally, I picked one of my vectors here, right? So what's going to happen is, well, if I is not 1, it's 0. If I is not 2, it's what? 0. But on the other hand, when I is I, I'll get that. I'll get CI, inner product VI, VI, needs to be 0. Well, the inner product with itself is not going to be 0. That can't be 0. So what does that mean CI is? And that is for what? Any I. So what does it tell you about all the constants? They're all 0. You just check. Oh, I'll take inner product V1, inner product V2, inner product Vn. Just do it for all of them. You'll find out, oh, C1 0, C2 0, C3 0, C4 0, and this thing completely falls apart. That's the idea behind it. You have to clean it up a bit. In other words, we have only the trivial solution. Now, the next one would be if V1, V2 up to VK is an orthogonal set. And the length of any of the vectors is 1, we would now call this a orthonormal set. Orthonormal sets are orthogonal sets. It's just that when I take the length of every one of them, I get 1. So if we go back to our one example, P1 was 1, P2 was x, P3 was 3x squared minus 1. What's the length of 1? It's going to be equal to what? The integral from minus 1 to 1 of 1 squared dx to the 1/2 power. Integral from negative 1 to 1, that's a rectangle of area 2, so that's just radical 2. What's the length of x? That's the integral from negative 1 to 1 of x squared dx to the 1/2 power. What's the integral of x squared? 1/3 x cubed. Plug in a 1, I get a third. Plug in a negative 1, I get a negative third. 1/3 minus a negative third. 2/3, radical 2/3. And then what's the length of 3x squared minus 1? It is the integral from minus 1 to 1 of 3x squared minus 1, the quantity squared, dx to the 1/2 power, which is integral from negative 1 to 1 of (9x to the 4th) minus 6x squared plus 1 dx 1/2 power, which is going to be equal to, these are all even, right? So I could just simply evaluate it, integrate it, evaluate it 1, and double, right? So this would be twice 9/5 minus what? Minus 2, and then plus 1. Which is what? 9/5 minus 10/5 is negative 1/5, plus 5/5 is 4/5, which is 8/5 square root. Were these orthonormal? What was the length of every one of these? Not 1. So on the other hand, I could say, if I would look at this, I would say, okay, but I do know. So P1 equal to 1 over radical 2, P2 equal to radical 3/2 of x, and P3 equal to radical 5/8 of 3x squared minus 1 is, that is orthonormal. Is everybody okay with that? Because I took them divided by their length, it's going to be length 1. Okay, now came what you were asking, well, don't these form a basis? And the answer is yes. If you're given, say, U1, U2, up to UK, and orthonormal set, then by that theorem that we have, if they're orthonormal, they're orthogonal. If they're orthogonal, that means they're linearly independent. If they're linearly independent, that allows us to talk about basis. That says that these are a basis for the span of them. Now, if they were a spanning set for a vector space, that would be a basis for that vector space. But on the other hand, a span is a vector space. It's normally a subspace of something, but it's a vector space. So it would be a basis for at least the span of this. And what we would normally do is we would just simply call the, say, capital U equal to U1, U2, up to UK, and orthonormal basis. Now, if we didn't need the normal part, the orthogonal part would still be a basis. It would be an orthogonal basis rather than orthonormal. Orthonormal bases are nicer, though. All right. Theorem. U equal to this U1, U2, up to UK is an orthonormal basis. It's obviously an orthonormal basis of its span. So we don't normally say that. Then if it's an orthonormal basis for what it's spanning, and say of, we have an inner product space. Orthogonal wouldn't even make sense if we didn't have our inner product, so it's an inner product space V. Then if you have a vector that's in this space, then obviously that vector is equal to C1, U1 plus C2, U2 plus everything up to CK, UK. Another way of writing that would be to say that these are the coefficients of that orthonormal basis, right? This linear combination is made up of the coefficients, how much of the first, how much of the second, how much of the third, how much of the last, right? And they'd be those how muches form the coordinates. So these are the coordinates of that vector within this particular orthonormal basis. And one of the questions would be is, could you find the coordinates? Because when we did change of bases, we know how to do. But a question that we would have is, I got to figure out what are the coordinates so that I could, if I wanted to have this basis and go to standard basis, I'd have to multiply it by U inverse to do that, but I need the coordinates. Where am I to figure out where is it at within a standard basis? Well, to find the coordinates, all you have to do is take the inner product with your vector and then each basis vector one at a time. What is the angle, essentially, right? What is this inner product between the vector and the first basis? That's just going to be the coordinate of the value for the first basis. Then what's the v with v2? That'll be the coordinate of the other. So an example of that, if we wanted to be, we could say, hey, we had that P1 was equal to 1 over radical 2. We had P2 was equal to radical 3/2 x. And we had P3 was equal to radical 5/2 of 3x squared minus 1. This is an orthonormal basis for the span, but the span of this one would be P3, right? Because this would be constants x squared. So I'd be talking about anything within three-dimensional space. So if I wanted to, I could say, hey, what about the function 1 plus x squared? It is going to be how much of P1, how much of P2, and how much of P3. And those coordinates will tell you how much of this, how much of this, and how much of this. So how much of the first polynomial, how much of the second, how much of the third would get you the same thing as 1 plus x squared. Well, all I'd have to do is say C1 is going to be what? What does this theorem say? Take the inner product of, where am I looking? I'm looking at 1 plus x squared with, who am I comparing it to? 1 over radical 2. That's just an integral. To integrate negative 1 to 1 of those two multiplied. And that'll be the coordinates. What about C2? Well, what am I at? I'm at 1x squared, but I'm comparing it to what? Radical 3/2 x. How do I do that inner product? I integrate from negative 1 and 1 to those two multiplied. And then my last coordinate, how much C3 do I need? I need this 1 plus x squared times radical 5, that's not 5/2, 5/8 of 3x squared minus 1 equals, and still I have to finish each of those. And if I do those integrals, I get the coordinates. Seems to be a lot of work, and it would look pretty ugly compared to, why not just use 1 plus x squared? Why are you using these weird polynomials, P1, P2, and P3, when I go through it? And the reason why is, well, these polynomials are orthogonal to each other, and they're of length 1. There's nice properties of orthonormal things. What are some of the nice, we say we're using them, why would I want to write things in coordinates of orthonormal objects, right? Why use U, a set, an orthonormal basis? Well, the first one, it's a corollary to this theorem that we had, which was, if I have an orthonormal basis, if I have that, if V1 is equal to A1, U1 plus A2, U2 plus everything up to AK, UK. And I had some other vector, V2, is equal to, say, B1, U1 plus B2, U2 plus everything up to BK, UK. So I have these two vectors within my inner product space. And what I've done is I've resolved V into coordinates, we'll call them A, within the orthonormal basis, and I've resolved V into the coordinates, let's call them B, of the exact same orthonormal basis. So I found the coordinates. What are the coordinates in this orthonormal basis? What are the coordinates in this orthonormal basis? Now, it can be any orthonormal basis, but we're using the same for each of those. Then, if I would want to find, hey, what is V1 and V2 inner product? Well, normally what you would do is you would go back to, okay, what's my inner product? Am I going to integrate? Is this matrix space and I have to multiply all my positions and add them up and take the 1/2 power? Is this polynomial space where I take a sample of so many points? Right? You could try to do all that work, but all it ends up being is A1, B1 plus A2, B2 plus everything up to AK, BK. Which is, if you find its coordinates, what's its inner product? Take the coordinates of A transpose and take the coordinates in B transpose of that same orthonormal space. It's the scalar product of the coordinates of that orthonormal basis. So it ends up being that It goes all the way back to the beginning. I just need to know scalar product. It's like, well, why don't I? But I'm dealing with continuous functional space. Don't have to worry about it. Because all these inner products, if you think about it, all the inner products have been handled. How do I find the coordinates? I do an inner product. How do I find the next coordinate? I do an inner product. So I've already done all the inner products. I just have to mix their results. And it ends up that the mix is exactly the scalar product. So no more integration to do. If this was continuous functional space, you would just simply say, hey, find the coordinates, mix up those coordinates, and you can work it out. In other words, if I would go back to, say, this problem here, right? If I had function f was this, and I told you its coordinates, and I had function g, which was equal to a pi minus ex plus x squared, like that, right? And I would find its coordinates in this P1, P2, P3, and I would ask, hey, what's the inner product between f and g? All I would have to do is say, well, what are the coordinates for f? What are the coordinates for g? Do the scalar product. It's literally that integral. In other words, I can do an integral without doing the integral. If I told you the coordinates, you could say, it's going to be this integral, and that's one of the things they do in a homework problem. They say, hey, integrate this. And you look at it and say, well, that integral is actually an inner product. And I already know what the coordinates are, so therefore, boom, just jump straight to the answer. Don't do any integration. So that's one nice thing about it, is we can actually do an inner product by using only the coordinates. But that would also get to how long is V1? Well, let's square it so I don't have to worry about the 1/2 power. What is that? How would you normally have done this?
V1 transpose.
We would normally take V1 inner product, right? But an inner product says just use the coordinates. And so what do we really do? This is actually a1 squared plus a2 squared plus ... ak squared, which is really what did we do? We take the coordinates for V1, transpose it, the coordinates for V1 in that orthonormal basis. But the coordinates have to either be found or being given. So if I define my space with these orthonormal bases, it doesn't matter if you're dealing with continuous functional space, polynomial space, any space. The coordinates are all that matter. And then you can do magnitudes and angles by just using the normal scalar product of their coordinates. So that's why it's nice. Another property of this, though, is if we're looking at, for example, in Rn, if I would say Q is equal to, and I'm going to have Q1, Q2, up to Qn, and this has the Q sub I are in orthonormal set. So if I have an orthonormal set and we're dealing with not, we're going to throw away continuous functional space. I'm just going to look at Rn. So it's normal vectors. And I look at these vectors and they're orthonormal. That means every column is orthogonal to every other column. The length of every column vector is 1. So it's an orthonormal set. That particular collection actually has a nice property as a matrix. And if this is true, where these are an orthonormal set, we are going to call Q a, all right, if the inside of Q is an orthonormal set, what do you think we should call Q? That would make sense, but we call it orthogonal. And orthogonal matrix. I don't know why. Probably they don't want to mix up the word normal, since matrices are within matrix spaces, and if they're within matrix spaces with a particular inner product, they could be of length 1, and that would be a type of normal. They're probably trying to avoid that normal if I had to do a history study. But anyways, we call it an orthogonal matrix. So an orthogonal matrix components are actually orthonormal. So we have to be careful on the naming of it. So anyways, an orthogonal matrix is a bunch of orthonormal things. Now, to be orthonormal, what does that mean? That means that Qi transpose Qj, and I'm using transpose because this is normal Rn, that'd be the scalar product, is always going to be what? 0 if I doesn't equal j. On the other hand, what does it equal if it's Qi transpose Qi? It's what? 1, because it's normal. This is the orthogonal part. This is the normal part. That's why it's orthonormal. Given that, these two things would mean what if I took Q times its own transpose? Why would it be the identity? So Q itself is what? That's Q1, Q2 up to Qn, right? Or if I wrote it as rows, so I could do it that way, right? I could say that we normally go row down column. So this would be going across it. Let's do it that way. Might as well do it this way. So Q1, Q2, Qn. And this here would be what? Q1 transpose. And then Q2 transpose down to Qn transpose. And so this is n by 1, and this is 1 by n, so it's going to spit out a what? N by n. But so what's my first one? My first position is going to be what? Q1 transpose Q1. But what's that? 1. What would be the next position? Q1 transpose Q2, which is 0 because they're different, right? Different row, different column, and so that would be 0, and then it'd be all zeros, right? What would be the next row? It would be Q2 transpose Q1, which is 0, and then Q2 transpose Q2, which is 1, and then 0 and 0. And so what does this become? The identity, right? And so that means Q transpose Q, because their insides are orthonormal, is just the identity. Well, wait a second. If two matrices multiply and it spits out the identity, what does it say about those two matrices?
They're inverse.
They're inverses. Boy, that makes the inverse very easy to find. That's awesome. If you were given a matrix that was orthogonal, the insides are all orthonormal, how do you find its inverse? Transpose it. That's a whole lot faster than what we used to have to do. But this is only for orthogonal matrices. And actually, you could go through all of that. We actually have there's 4 properties. When you say the words orthogonal matrix, 4 things come along. 1, the Qi are, and its columns are what? Orthonormal. So not only are the columns orthogonal, they're of length 1. A second thing that comes along is what we just showed, that Q transpose Q is equal to the identity. But if Q transpose Q is equal to the identity, that really means that Q inverse is simply Q transpose. But the other thing that would happen on that would be if you would take Q applied to X and Q applied to Y and ask for its inner product. So Q itself is a matrix. And if Q itself is a matrix, that means that it's actually a transform. So QX is a transform and QY is a transform. If this is true, it ends up being that this would be just simply X, Y. So that tells you that angles and lengths are preserved by orthogonal matrices. So if you multiply things by orthogonal, it's a linear transform. This linear transform will preserve lengths. It'll preserve angles. And the fifth here is that, have a little bit of a definition here, which is called the p-norm, which is one way of calculating lengths. Our normal way of doing a length was, hey, what's the length of x? Well, that was just equal to x to the 1/2 power. Well, what is that? That's x1 squared plus x2 squared plus everything up to xn squared, all to the 1/2 power. One of the things that happens is we could kind of play around with doing different norms. A p-norm is to say, hey, how long is this according to p? What is that? You take the magnitude of x to the pth power, and then x2 to the pth power, plus everything up to xn to the pth power. We take absolute value in case we have issues, and then you take 1 over p. In other words, the normal norm that we normally think about, this x to the 1/2 power is normally called the 2 norm. It's the square root of the sums of the squares is called the 2 norm. The cube root of the sum of the cubes absolute valued is the 3 norm. The fourth root of the sum of the fourth powers is called the 4 norm. What happens here is the 1 norm is just the sum of the absolute value, takes the maximum of those, and the infinity norm says if these go to infinity, it just simply the infinity norm says if this goes up to infinity, the only one that would matter would be the term that is largest, and so that would pick out the max. And so you can do 1 norms, infinity norms, and then any norm in between. So normally what we've been talking about is actually the 2 norm, and you'll see that in the text. And so that says that the length after the transform is the same as the length before the transform according to the 2 norm. Again, all that says is a matrix that is made up of orthonormal columns will leave lengths alone and leave angles alone. It'll transform things, but lengths will not get longer or shorter, and angles will not change in terms of that transform. Any matrix that has its columns this way will preserve that. And that lastly is where we'll stop here and we'll talk about the least squares problem again. The least squares problem was ax equals b is overdetermined, and the rank of A is equal to n. We have no free variables. So I have an overdetermined system and no free variables is how this was understood as Rn. How did we go about doing a least squares problem? The least squares problem was that A transpose A x hat is a solution to A transpose B. Now, on the other hand, if A was made up of columns, right, that were all orthogonal in length 1, what's A transpose A going to spit out? The identity. And so that would mean that if A is orthogonal, that implies that A transpose A is simply the identity. So that says that the least squares solution x hat is simply A transpose B. We can use this part, and we'll actually extend this out to all vector spaces. And in particular, in next class, or at least for the first part of it, what we'll talk about is vector spaces of functions. And what we'll do is we'll talk in particular about, what is this doing? This is projecting, right? This is this idea of B being solved and trying to find the nearest thing that gets you close to B without working it out. And where this gets to is the following. Continuous functional space has an infinite basis. But if you want to work with functions, you need to have a finite basis. But a span of a finite basis is obviously not going to cover all continuous functions. So that's what we're going to do. We're going to take all functions and cast them back to a span that's nice to us by using just the least squares problem. All right, that's it.
I have a question for you.
Yep.
So if